Okay,
Good morning,
recording is
Ashish.
on. Yeah,
Sir.
yeah. Good morning, folks in Bangalore. Good afternoon, folks in Sydney. Thanks for your time. Um, so, who, folks, whoever are not talking, I would request to go on mute. Okay, I have muted all of you who are not talking. So, Spitfire is, very important topic for all of us. May it be support services, the deployment and planning, or maybe BCS teams in professional services. Everyone, it's important. So we're starting off this series of trainings. You know, uh, we're trying to collect the sources where like NPIs and other trainings and try to customize trainings towards our needs. So in this series, this is the first one. Um, most of you may be knowing Anil. So he's one of the senior engineers in the Microsoft Cell team, and Microsoft deployments. They are like uh, setters or the pace setters. So Anil, hand it off to you. So this is the introduction section. So we did a couple of weeks back. So it's kind of a repeat. If you guys, some of the guys have already attended the previous one, it's kind of a repeat one, but it'll be a good start. So Anil, over to you.
Okay, thank you, Ashish. Hello, everyone, and welcome to Introduction to Cisco 8000 Series Router. Myself, I am Anil Kumar Dantu, and I'm part of HTTS Microsoft Shell team. So this is, as Ashish just mentioned, this is the first training module as a part of the Spitfire ramp-up training sessions that Ashish, Ruchir, and Shashank has got together and planned for the team. So this is the first session, and we would be conducting similar sessions every Monday for the next 6 to 8 weeks. So in the agenda of the session, we will be starting with Cisco 8000 hardware architecture. We'll go through various components like the RP, line card, fabric card, BMC architecture, and also go through power, fans, and EMON, like power modules, fans, and EMONs. And we will during the session, in case you have any questions, please feel free to interrupt me, and we can take the questions during the session itself. Okay, Cisco 8000 series hardware architecture. Okay, so Cisco 8000 router is the flagship product from Cisco. Like it's a new product line from Cisco, and it is actually positioned as a LSR router in the MPLS core backbone. It is also positioned as an aggregation router in the ISP as well as in the data center domains. Also, it is positioned as an internet gateway router. So as of today, this product is getting positioned in three roles. That is as an LSR, that is label switch router in the MPLS core. It is positioned as an aggregation in the data center, like aggregation or as a regional aggregation or the aggregation router in your leaf spine architectures. Also, it is positioned as an internet peering router. So currently it is not positioned as an edge router as of now, but in future we might see in the similar roles also. So the 8000 series router is available to us in two form factors. One is a fixed chassis, and another is the modular or the distributed system. So in fixed system, you have two models, and actually the fixed system, they start with the series of 8200. So you have 8201 and 8202 in the fixed form factor, that is fixed chassis, while on the distributed system or the modular systems, you have the series starting from 8800. Okay. So you have 8808, 8812, and 8818. Plus, you also have 8804, which is not yet FCS, but you might see it in near future. Okay, and with regard to throughput, this could, like it starts from 10.8 Tbps on the fixed chassis system, and it goes all the way up till 260 Tbps. So it's in terms of traffic or the bandwidth handling capacity, it is one of the highest that is available among the Cisco products. Okay, so the fixed system, that is 8201 and 8202, they are actually a single NPU system. Like there is only a single chip on, or you can call it as a system on a chip architecture. Like all the optics, they connect to a single chip, and that's it. And then there is a local CPU to run your XR image, and there is no other hardware in it. Okay, so very simple as an architecture, but though it has a single chip, it has a throughput of 10.8 Tbps. While plus it supports 400 gig ports. Like on a 8201, you have 24 400 gig ports and 1200 gig ports. Like, so it's a huge number of, like with regard to port density as well as the throughput capacity. But coming to the distributed system, that is 8808, 12 and 18, your the series is like 8808 means it has 8 line cards. 8812 means it has 12 line cards, and 8818 means it has 18 line cards. Okay, so wherever the last number is, it is representing the number of line cards the system is having. Okay, and in the distributed system, as of today, we are supporting 2 types of line cards. One is a 48 into 100 gig port line card, and second is a 36 into 400 gig line card. So 2 variants are available to us right now. And if you just see a comparison of the similar platform with other Cisco products like ASR 9K or NCS 5500, you can see on comparison basis, these are the lowest power consuming product. Per 100 gig port, the power consumption is approximately 4 watts. So it is one of the lowest in the industry. Okay. And this product is actually positioned for both like a data center of our web customers as well as for the service provider customers. So coming to the key differentiators of Cisco 8000 series platform. So what differentiates this product with our other products from Cisco? Like we have ASR 9K, you have CRS, you have NCS 5500. So how it is different? The first and the major differentiation is superior silicon. Like this would be the first Cisco product which would be using the Cisco Silicon One ASIC, also internally named as specific ASIC. So it would be the first platform which would be using the Cisco Silicon One ASIC. Now, what is the key benefit of this chip? Like it is the first routing chip in the industry to cross 10 Tbps barrier without compromising on bandwidth, without compromising on major features, power efficiency, buffering, programmability. So without compromising on the flexibility, this is the first chip in the industry which provides this high throughput of 10.8 Tbps. Apart from this, the Cisco 8000 series platforms have architecture longevity. What do we mean by this? See, it's not just about like the product support from Cisco lasting for 10 to 15 years. The product at the start provides you 400 gig ports at the launch of the product. So as then the further development takes place on the ASIC and on different line cards, we will have 800 gig ports, 1.6 Tbps ports, and further on. So this is just the start of the product. Like we'll have further developments and further products, like different product types getting launched across. So this is good enough to support the service provider as well as the web customers for the coming decade. Plus, it uses XR7 as a software, which is new. So it is also called as Link, LNT. So which so it is traditional classic XR or EXR. Plus, it it addresses long-standing customer complaint of not having a Linux, rather than having a Linux look like XR. They want XR to be like Linux. Okay, so they don't want just a look like a feature or system, but it should support lot of Linux command lines and tools and all those stuff. So that's what XR7 addresses. It is modular and lot of features are there. Okay, and next it is trusted platform. Trusted platform is with regard to security features. So this product is part of the Cisco trustworthy profile. Means the hardware chips are having integrity checks as well as anti-tampering checks and those stuff. So this is the new feature that is getting integrated in the Cisco hardware. Not just in hardware, also during software boot up, it makes sure that the image is signed, there is no corruptions as such, and no tampering or such things. Plus, it also secures your boot, like your storage. Even the storage system on the platform is secured with these features. Plus, this product supports network disaggregation. Like it will be the first router which we would be offering as a product for network disaggregation. As of today, we have Nexus products like Nexus 9200 and 9300 series products, which are offered for network disaggregation, where customers can use our Nexus hardware and install their own software like Sonic or EBOS or their own custom software they can install on Cisco hardware. But this would be the first router product which they can install the software. Ashish, I'm just getting some things like, can you paste the Spitfire link, like training link? We are not able to join the session, looks like.
Okay. So where, who's playing?
1 minute. On the chat. Just a minute. I'll just stop sharing for a brief minute. Actually, I'll just paste in the link. Okay. Apologies for that. I'll just share it again. Okay, so this is the first Cisco router to be offered as a network disaggregation product. Like customers can install their own software on this product. Rather than using XR, if they have their own software image, they can install it. Like Microsoft is planning to deploy Sonic image. Like there are other customers who are planning, like Facebook has their own image at Boss. So they can install such images on this product. So definitely it has to be certified by Cisco and for the support, but the product does offer capability of installing non-XR image on the product hardware.
Hey, hi, I have a question. How many software are officially supported as of now?
See, as of now, Sonic is supported. There was all, and it is supported in fixed platform, and it was even demoed for the distributed platform. Okay. Plus there is, as of now, that is what I'm aware of. This thing, but the other customers can approach Cisco for support of their software image on the product.
Okay, thank you.
Okay, so actually at the core of this product, the most important part is the Cisco Silicon One ASIC. Okay, And the key highlight of the ASIC is it is very flexible. Okay, so coming in the next 3-4 slides, we will be discussing about Cisco Silicon One ASIC, and we will understand what actually makes this chip so flexible. Okay, so historically, all the network chips that are available, either made by Cisco or available in the market, they are actually customized for every usage. Like for access equipment, you have a specific chips. For edge routers, you have specific chips. For core routers, you have a specific chip. For internet peering routers, you have a specific switch. Or even for a web customers, they have a specific, like a switching chips they have. So Cisco's this Silicon One ASIC, or internally coded as Pacific ASIC, actually it actually touches all the requirements that are typically web customers and a service provider customers have, and gets the best of the both worlds. Like this chip can address the requirements. It's flexible enough, and it can be programmed to act as an access device chip. It can be programmed to act as a core device chip. It can be programmed to act as a internet peering chip. In future, we can also program it using for the edge device applications also. Okay, as of now, that support is not there, but in future it can be done. Okay, so what actually makes in the normal router hardware, like you will be having a lot of hardware module profiles, right? So you can have a lot of profiles made available using which you can program your chips or the NPUs for the respective applications. Okay, some profiles are by default based on the product, and some are user defined. Okay, like user can select them. So this is the Cisco Silicon One ASIC. Is the main advantage is it supports across the spectrum, whether it is access, aggregation, edge, core, and all. Plus, it has the best offering with regard to low power consumption, highest port density, scale. The scale is the best available on a routing chip in the industry. Plus, plus with regard to not just programmability and large buffering for the packets. Okay. So it's one chip which comprises all these features. Earlier, the similar features were available on individual chips which were customized for each application. Okay, just an example. Say we have Lightspeed chip in ASA 9K on the extreme left, and you have your Tomahawk 3 or the Innovium chip on the right, on the extreme right. Okay, so a Lightspeed chip is actually custom made for edge routers or the routing applications, while the Tomahawk 3 or the Innovium chip is basically chip customized for the switching or the data center or the web scale customer applications. Okay, but each of this chip actually compromises or has a strength on few domains. Like a Lightspeed has a strength with regard to chip table sizes. It has good stacks, good buffers available for the stacks. It is flexible with regard to what profiles you can add on it or new features you can develop on it. And QoS support, it has very granular QoS support, and it has large buffers. But with regard to bandwidth and the packet processing capability, it is on the lower side. Plus, on the power usage, it is a little bit on the higher side. Okay. So similarly, if you go to the extreme right, that is in Tomahawk 3 or the Innovium, it has very good power, like very low power usage. It has good bandwidth and packet processing capability. Plus, it has high port density, but it lacks with regard to the script scale, the stacks, counters, then flexibility. Like you can't program or have too much features developed on it or deployed on it. Plus QoS features, it is very restricted. Plus it has low buffering. So there is based on the application, the chips were designed. But if you compare the central, the chip, that is Cisco Silicon One, you can see it is actually taking the best of both the worlds, the routing world as well as from the data center switching side. So it is very good with regard to low power consumption, high bandwidth, and high port density, high packet processing capability. Okay, like this is, I'm talking for the chip, individual chip, not at the product level. Okay, plus it has good fit scale. Okay, like it can handle easily 7 million V4 routes or 3.5 million V6 routes. So the fit scale is decent. I won't say it is as good as we have in ASA 9K products, but it is pretty decent. Plus, it is lacking little on the stats. The number of stats counters that are available are limited. Plus, on the flexibility side, it is like you can develop features on it, but it is a little bit less as compared to your 9K and as well as the QoS queues. You only have 8 queues available for the QoS and the related counters. Okay. So it tries to take both the best from the both routing and the switching world. So this diagram it is actually counting from 0 to 10, and it is actually rating the chip on the scale of 0 to 10 with regard to each of these features. Okay. So any questions until now? Okay. So as I mentioned, the Cisco Silicon One is ASIC. It actually is twice the bandwidth of the best available routing ASIC available in the industry. Okay, and it is the first routing ASIC to break the 10 Tbps barrier. Okay, so individual ASIC NPU can handle 10.8 Tbps of traffic. So it is the first chip to do that, and it has higher packet processing capability, 3 times than the best other available chip in the industry. High route scale. It has a pretty decent routes in-chip memory to handle the FIP tables, your TCAMs, your packet buffers, and those stuff. So it has high route scale, deep buffering. It is very power efficient for 100 GB traffic or the port. It consumes around 4 watts of power. So it is lowest in the industry. Plus, it is very programmable. Like this chip, you can program it based on your based on the product or based on the requirements. Okay. So
yeah, just a comment on the programmability, right? It's a P4 programmable. So for the fib, for the fabric role or for the line card role, we have the same ASIC, right? You just need to program the ASIC if it's for fabric role or for line card role. So that's how it's so flexible.
Yeah. Say it's like you have a single Cisco Silicon One or the specific ASIC, which you can program it in 3 different roles. Like on the same chip on a fixed system acts like a system on a chip. Okay, like if there is only one chip with optics connected, and that's it. There is everything the chip does it. There is no external memory and those stuff. So everything the chip is doing, and all the hardware or every component is inside the chip. Okay, so that is in one role. It is a system on a chip architecture. Apart from this, you can use the same ASIC, the Cisco Silicon One ASIC, in a line card where it can do dual roles. It can act as a network-facing interface. Also, it can act as a fabric-facing interface. Okay, like in earlier products, you used to have separate chips for the NPU and separate chips acting as a FIA, right? So here is the single chip which is doing that role. Okay. Plus, the same chip can be used in the fabric card, acting as a fabric element. Okay, so same chip you can program as a system on a chip. You can program as a network-facing interface, as a FIA. You can also program it as a fabric element. So you can use it in 3 different roles. Okay. So, and one more important thing or the comparison with the earlier platforms is this Cisco Silicon One chip actually uses run to completion method of packet processing. Okay, like you had your traditional other products like few systems in ASA 9K or few in NCS 5500, they used to use the pipeline model of packet processing, but Cisco Silicon One or the Pacific ASIC actually uses run to completion mode of packet processing. So what is the basic difference between the two? In run to completion, it actually, in case you have a packet which has low feature or low processing that is required for the packet, then that packet can be processed very quickly. And in case you have a packet which has complex forwarding decisions to be made, like lot of features, lot of headers on it, then it will take a little bit more time as compared to the simple forwarding packet. Okay, while in case of a pipeline, irrespective of the packet, like whether it's a simple forwarding packet or a simple forwarding lookup packet or complex forwarding lookup packet, it will take same amount of time in a pipeline architecture because it has to pass every stage of the pipeline, right? So it doesn't differentiate between that. While here a simple packet can be processed very quickly, a complex packet will take some extra time. So the time difference gets compensated, and as the chip itself is very powerful with regard to processing the packet, like it has high PPS per second. So it can achieve high throughput of almost 10.8 Gbps. Okay. So it has all on the chip itself. It has all your the TCAMs to handle your SIB, your ACLs, your packet buffering. Plus, it has an extended buffer also in the chip itself. So, like you had in your NCS 5500 or other platforms, where you have on-chip memory and off-chip memory, here there is everything is inside the chip itself. So it doesn't have to leave the chip for processing the packet. So that way, it is able to achieve high throughput and high processing from the packet. So coming to one important point with regard to the ASIC. So this is an ASIC diagram with regard to system on a chip. Okay, so typically on your fixed systems, you will have a single NPU. Okay, and this is an internal diagram of the NPU, where the single NPU is actually divided into 6 slices. Okay, so you have 6 slices. And each of the slice, they act as a network facing interface. Okay, so all your optics are connected to the slices. Okay. And you have your local CPU where you will be installing your XR image, but all your packet processing and those stuff will be done by the NPU itself. Okay. And there is no fabric or nothing. So this is like the NPU is acting as a system on a chip. Plus, you have a couple of terms that we should be aware of. Like apart from slices, you have interface group that are there. Like a set of interfaces, they form an interface group, and there are 2 such interface groups are allocated to a slice. Okay, so and each slice can handle 1.8 Tbps of bandwidth. So you have 6 slices. So 1.8 into 6, it is equal to 10.8 Tbps. Okay. So all your interfaces, they would be grouped as an interface group, and a set of 2 such interface groups will be part of a slice. And you have 6 internal slices in your NPU. So you can consider your slice as a micro, like a micro core or the cores. Like you have your multi-core processors, right? You can consider your NPU, this particular NPU as a 6-core NPU. Okay. So each core has equal access to the memory, the tables, and all that. Okay. So this is one way of programming the chip, where you program all your the NPU and the slices inside it as a network facing. Apart from that, you can program your in a line card. You can program few of your slices, like these slices. You can program them as a network facing interfaces or the network facing slices, and another set of 3 slices you can program them as a fabric slices or the FIA. Okay. So similarly, on the other line card, you have fabric FIA slice, and you have your network-facing interface slices. On a fabric card, all the 6 slices, they are programmed as a fabric element. Okay, so this is the same chip is now is available to you in 3 different roles, like a system on a chip, where all the slices inside the NPU are programmed as a network interfaces. In a line card, few slices are programmed as a network, few slices are programmed as a fabric interface ASIC, and in a fabric card, all the 6 are programmed as a fabric element. So just like in a fixed system, you just have your Pacific or the Cisco Silicon One ASIC, and you have a local CPU to install your XR image, and your optics directly connect to the Pacific ASIC. While on the distributed system, on line cards, you have your Pacific or the Cisco Silicon One ASIC, and on the fabric card, you have the Cisco Silicon One ASIC acting as a fabric element. On the line card, the same ASIC does dual roles or network interface as well as the fabric interface ASIC. So it is one chip which is used in multiple roles. Okay. So before we get into details of each of the fixed and the distributed system, any questions up till now?
Hey, hi, Anik. Am I audible? Hello.
Yeah, yeah.
So I have a query. So basically, on the line cards, we will have to configure the the ASICs equally between fabric element and the network facing element, right? Well, basically interfaces. So as we have the full throughput.
Actually, see, yeah. Actually, you install your software on the CPU, right? And then that software is loaded on the NPU. Okay. Now, based on the system, like say in case it's a fixed chassis system, system, then the NPU will get programmed as all network facing interfaces.
Okay.
In case it's a line card, it will program its chips, the NPU, and the slices inside the NPU, slice 0, 1, and 2, as a network-facing interface. Okay, it will get programmed, the slice 0, 1, and 2 as a network-facing interface, while the fabric-facing slice, that is 3, 4, and 5, will get programmed as a FIA.
Okay.
Now, in case it's a fabric card, then all the slices will get programmed as a fabric element.
Okay. So is that configurable? Yeah, I got your point. So is that configurable? No. Like, no, right? Okay.
No. Not by us, but like for example, as I mentioned, this product is available even as a DISAG, right? Network disaggregation. Now it is up to the customer to how they want to program his slice. So based on the image he is trying to install, the slice will get programmed.
Okay.
But in the current offering or in Cisco 8000 series, in a fixed system, all the slices will get programmed as a network. On a line card, 3 as a network, 3 as a fabric, and in fabric card, all 6 as a fabric. So they will get automatically programmed.
Okay. Thank you.
Okay. Now let's go to each of the products. Okay, like just we'll have an overview of each individual products. We'll start with the fixed system. So in as I mentioned, the fixed systems, they will start with 8200 series. So right now we have 8201 and 8202. Okay, so they though they are like 2 different platforms, but they have a single NPU in it. Okay, there is only one Cisco Silicon ASIC in both of these platforms. Okay, only difference between these 2 platforms is the port density. The 8201 is having 24 400 gig ports and 1200 gig ports, while the 8202, it has higher port density, but like it has 12 400 gig ports and 60 100 gig ports. So if we do the max, it comes around to 10.8 Tbps. Okay, so it is a single chip and with the optics connected and has a local CPU and the memory for installing the image. So it's a simple architecture with power supplies and the fans. That's it. So single ASIC. So it has we also call it as a system on a chip architecture, and it has a 10.8 Tbps of traffic handling capacity, and it supports both 400 gig as well as 100 gig objects. So for 400 gig, for a few of the ports are actually you can identify from, like, for example, on 8202, whatever you can see as highlighted in blue, they are all 400 gig ports, while the others are 100 gig ports. Similarly, on 8202, the one highlighted on blue are 400 gig, remaining are 100 gig. So this is the front and the back side of the chassis. Like you have your dual power supplies and the fans on the back, plus the console and the USB boot and others. This is the diagram for the 8202. It has again 2 power supplies, 3 fan modules on the back, and the ports on the front side. So one advantage or one main benefit of this product is it has very low power consumption, okay, for this product. As you can see, it is as low as 4 watt per 100 gig. For this, it is 7 watt per 100 gig. Okay, so the fixed systems, they use the Intel Broadwell CPU of 2.4 gigahertz. It has 32 GB of memory. It has 128 GB of hard disk, and it has our standard console, USB ports. Also, there is one difference that we should be noticing is it has a BMC port on it. Okay, this is the Cisco 8000 series is the first platform on with regard to router series to have a BMC port on it. Okay, so we will talk about BMC. We have 3-4 slides about it, and it supports secure boot and other security features.
Anil, just one question from your previous slide. So the power supply which you mentioned, are they modular and hot swappable?
Yeah, actually, yeah, they are hot swappable. The fans, I need to confirm on power supplies. This thing, fans are swappable. Power supplies, I just need to double confirm on this.
Okay.
The fans are hot swappable. Okay, and this is one sum for 8201, which has 24 400 gig ports and 1200 gig ports. This is just explaining how the ports are assigned to interface groups, how interface groups are part of a slice, and how these slices are part of the NPU. So it just shows the hierarchy. Okay, you have your interfaces, which are part of the interface group. Then these interface groups are part of a slice, and how each slice forms a whole NPU. Okay, so here as I mentioned, each slice will have 2 interface groups, interface group 0 and 1. Okay, then you have total 12, 0 to 12, 6 interface groups would be there. Okay, then each slice will have 2 interface groups. Okay, and for this is for 8201. So it will have 2 400 gig and 100 gig ports, like 2 400 gig interfaces and 100 gig interface. This would form one interface group, 0. The another second 2 into 400 gig ports and 1 into 100 gig port will form the interface group 1. So these whole 0 and 1 interface groups will be part of slice 0. Similarly, that's how the ports gets allocated. Now, if you do show controller, NPU, VOQ usage, interface, all instance, all location for the RP. Now, this is a fixed system, so you can treat it as RP. Okay. So there, if you see, each of this interface would be allocated to NPU 0 because it is a single NPU system, so you will have only NPU 0. Okay. All interfaces would be part of NPU 0. Then, based on the core, like now NPU core is nothing but your slice. Now you have 6 slices on the NPU on the fixed system. So your slice, the core number will change from 0, 1, 2, 3, 4, and 5. So you will have 6 slices. Okay, and each slice will have 2 interface groups, 0 and 1. So that's how you read this info. So, so there is one more information, like each of the slices, right? So as I mentioned, each of the slices, they have equal access to all the shared memory. The shared memory, the buffer, the TCAM, and the tables and all. So each has equal access to all the memories. And inside the slices, actually, they call it as NPEs, network process engines, running inside the slice. Okay, so each of these network process engines which are running inside the slice would be running your actual run to completion code or the packet processing code. Okay. So inside each slice, you will have multiple network processing engines, okay, which are running software codes.
Anil, in this output, you mentioned that each slice will have an interface group which contains 2 into 400 and 1 into 100. The output, what I could see on the downside, the show control NPU, VOQ usage. So that 0 has contained 400 interfaces. I don't see any 1 over there. So how to interpret this actually?
Okay, so your NPU is 0, then NPU code
Right.
is your interface group. Okay. Okay. So that is having 400. Okay, this is 1, 2. See, now this one and this one is 400 gigs, right? 400 gigs, which is having these are part. This is 0 is of slice 0. Okay, NPU 0, slice 0, interface group 0. Okay, NPU 0, slice 0, interface group 0. So 400 gigs are gone. Okay. Now,
so PP port is the interface group.
Yeah, correct.
Okay, got you.
Okay, so that's how you read it. In case when you are troubleshooting it, you see whether they are associated with a single NPU, then inside which slice, so you can troubleshoot in that way, and whether they are part of a single interface group.
Okay, fine. Thank you.
Okay. So any questions on the fixed system? I'll get back with regard to whether the power supply modules are OIR capable or not, or they are fixed with the channel. We'll make a note of. Okay. Now coming to the distributed systems. So in the distributed systems, we have 3 variants as of now. But as I mentioned, 8804 would be going FCS in some time later. So as of now, we have 3, that is 8808, 8812, and 8818. So wherever the last number indicates the number of line cards the chassis can support. Okay, 8808 will support 8 line cards, 8812, and 18 will support 18 line cards. Okay, on line card types, we have 2 variants of line cards. One is 36 into 400 gig, and second is 48 into 100 gig. So 2 different variants of line cards that are available as of now. Okay. At the top of the chassis, you have your power trays and the power modules inside that. Okay, so these are at the top you have 3 power trays, and inside each power tray you can have power modules inserted. Okay. Next, below the power tray, at the top you have 2 RPs. So your RPs are half slot systems. Okay, so this is RP0 and this is RP1. Okay, so on the same slot you have 2 RPs because they are half width cards. The 2 RPs, and then rest they are all line cards. Okay, from depending on the system, like 8 line card system, it will have 8, 12 will have 12, and 18 will have 18. So on the front you have your RPs and your line cards. But on the back side of the chassis, you will have your fan trays and your fabric card. Okay. So I just want to make a quick note. See, if you had worked on NCS 5500, these products are very similar to NCS 5500 with regard to architecture, CLI commands and all. But if you have worked on ASR 9K, then there is slight learning curve with regard to these products. Okay, like especially with regard to CLIs and the troubleshooting. And one more difference, like if you get with regard to NCS 5500 and Cisco 8000, this product doesn't like in Cisco 8000 we do not have shelf controller card. Okay, all the shelf controller functionality is now put back into the RP. Okay, you don't have any dedicated shelf controller card in the chassis.
Anil,
So
on the time check, we just crossed halfway mark. Just for information.
yeah, I think we are good, Ashish.
Okay, thank you.
We are just crossed half an hour, right?
No, 45 minutes, halfway mark we crossed, so 45, 40, almost 40.
Okay. Fine. I think we should be good. We should be good. This is the photo of the chassis. Like you can see, there is no backplane with regard to, like as I mentioned, at the top you have your power supplies, your power trays, then you have your power modules, then you have your RP slots, and on the front side you can insert your line cards. While on the back side you will have your fabric cards and your fan trays. Okay, so your line card and your fabric card will be mating without a backplane as such. There is no backplane here. Like the cards will be mating directly. Okay, like vertically and horizontally, they will they will have a separate diagram for that. So this is how the blank chassis looks like. Okay, so now this is one more diagram which shows your power modules, your RPs, and your line cards. And this is the back side of this. Like you have your 4 fan trays on the back. So you have to pull out the fan tray to access your fabric cards. So behind each of the fan trays, you will have 2 fabric cards. And the fabric and the line card will be mating directly. Like there is no backplane as such. Okay. And this is just the show platform output of the router. One more thing to note, there is no admin mode here in XR7. So we will cover more details when we will be taking the software architecture session. Okay, so now we will discuss individual cards. Okay, RP, fabric card, line card, then BMC, optics, fan tray, power modules, and those. Okay, so your RP has a 2.4 gigahertz CPU, which is an Intel Broadwell CPU. It has 32 GB of memory, 128 GB of hard disk. Plus, it holds the UOBC switch, 10 gig Ethernet UOBC switch, which interconnects your line cards. Okay, your RP and the line card for the control plane or the front-end inject traffic or for image downloads and those stuff. It uses this UOBC switch. Okay, so your RP and the line cards are connected via the UOBC. Okay. Apart from that, there is P2PM connection between the RP to LC, FC, fan trays, and the standby RP. Now, what is this P2PM connection? This is the connections from the RP FPGA to the FPGAs on the line cards, your fabric, and the fan trays and other systems. So your RP controls the other cards using this P2PM connection. Apart from that, you have PCI connections from the RP to the fabric card. Okay. So one important difference to note in a Cisco 8000 series router, on the fabric card, there is no processor. Okay. So it uses the CPU of the RP for the processing function. Okay. The fabric card only has NPU. There is no CPU on the fabric card. So the fabric cards are connected to the RP CPU using the PCI connection. Okay, so there is a PCI switch which connects the fabric cards. So the NPUs on the fabric card will get programmed directly by the RP CPU. Okay. Plus it supports the secure boot and the chip guard and those stuff. Plus it has a BMC interface on the RP. So this is the just the diagram of the RP. Like it has a standard console. It has a USB port. Okay. Plus it has a BMC port. We will talk more on during the BMC section. Plus it has a management Ethernet. Plus the clocking and the signaling and those things. So you can, this is another diagram of both the RPs. As I mentioned, they are half slot on this thing. And when you do show platform on the RP, it has active RP, plus it has a BMC 0. Okay, so you will see this is something new. Like an RP will have a CPU, okay, which runs XR, plus it will have another component called as BMC. Okay. So we will talk during the BMC section on it. So this is one notable difference that you will see for the RP when you do show platform. You will have a 0 RP 0 CPU 0 plus 0 RP 0 BMC 0. Plus the other commands are pretty much similar, like show file system, show media, so normal typical XR commands. Okay. So this is the high-level dot diagram of the RP. Any questions?
Yeah, Ashish Anand had one question. So Ashish, so fabric cards do have a CPU, okay, and we'll have a detailed section on troubleshooting fabric. So the commands are similar to what we have in Freta. So.
Okay. Okay. Got it. Thank you.
See, now this is the block diagram of each of the cards. Now this is the RP, then you have your line cards, and you have your fabric cards. Okay. So we can see from the on the RP you have an EOBC switch, okay, by which it is connected to the EOBC switch on the LC, okay, which is used for all your control plane functions, like your punt, inject, as well as image loading, image copy, and those things. Okay. So this is the connection that is used for. So it is pretty much same like we have in NCS 5500, similar VLANs, and like you have your show controller switch, right? So similar commands, they work for this, which is used for connectivity between LC and the RP. Plus the RP has a BMC port. It's a dedicated, it's a separate chip on the RP. Okay, so we will talk about BMC during the BMC session, but there is a separate ASIC for BMC on the RP. Plus there is a PCI switch on the RP, which is used to connect the fabric. Okay. So fabric is connected via the PCI switch, and the NPUs on the fabric, they talk to the RP via the PCI switch. Okay. So they download, the NPU get programmed via the PCI switch from the RP. Okay. And RP actually controls your power trace and your fan trace. And they do using the there is an FPGA chip ASIC on the RP via which it controls the power trace, fan trace, your line cards, and the fabric cards. So this is one more diagram for the RP. Like you can see different connectivities. Now see on the chassis we saw actually there is no backplane, right? So actually that statement is true with regard to data traffic. When traffic has to go from your one line card to another line card, it goes via the fabric. So there is a direct meeting between the line card and the fabric. But when like a punt and inject traffic or control plane traffic and other like image download and communication between the RP and the line cards, that all happens via the MIPD. So that is there on the chassis. So your RP actually controls your power trace using the PM bus. Plus, it controls your LCs and the FCs using the P2PM connections. Like the FPGA on the RP actually controls the line cards and the FCs using the P2PM connection. Plus, all the clocking information, like in case you are using any clocking and timing interfaces or getting time from the line and passing on to the RP. So the same P2PM connection would be used for that. Okay. For the data part, the RP is not in the picture. It is directly between the line card and the fabric card. So that's right. any questions on this? And as I mentioned, you have your fan trace on the back side and you have the fabric cards. So you have to remove your fan trace to access your fabric cards. Now coming to the line card, so you have two variants available with regard to line cards. That is 48 gig port line card and 36 400 gig line card. Okay, so you have two different variants available. So plus it does support your normal optics breakout, like you can have breakout on a 400 gig port. You can break it into two 200 gig ports or four 400 gig ports and further. So those are all supported. Okay. And each of the NPU actually has an 8 GB memory in it. Like it's an on-chip memory. They call it as a high bandwidth memory, which is apart from the small internal memory on the chip. So on the chip, actually you have two memories. One they call as a shared memory block, which is of 36 MB, and you have an HBM memory, which is of 8 GB. So you have two memories on each of the NPUs. And the line cards are common across your products like 8808, 12, and 18. Okay. And the 48 into 400 gig card actually supports MACsec, while 36 into 400 gig card doesn't support MACsec as of today. So coming to 36 into 400 gig card, so it has 4 NPUs on the line card. Okay, so it has 4 Cisco Silicon 1 ASIC. So 9, like it has 36 ports, right? 36 into 400 gig. So 9 interfaces, 9 400 gig interfaces are assigned to a single NPU. Okay, so similarly, you have 4 different NPUs. Okay, and one restrictions with regard to 36 into 400 gig card, working to 8 fabric card mode. Okay, so the Cisco 8000 series router runs in 2 different modes. One is 5 fabric card mode and 8 fabric card mode. The default is 8 fabric card mode. So for a 36 into 400 gig card to boot, the system should run in 8 fabric card mode. Okay, and 8 fabric card mode doesn't mean that you must have 8 fabric cards. Okay, you can have less number of fabric cards, but the mode should be set into 8 fabric card mode. We will talk about it during the fabric section. So this is the information with regard to the line card. So it has 36 into 400 gig card, 4 NPUs. It has some retimers, like some of the NPU are a little bit away from the optics. Like there is some distance between the optics and the NPU. So there is a retimer ASIC which actually does an amplification function. So one of the NPU will have that retimer. Okay. Plus it has a P2PM interface to the RP for the FPGA interaction. Okay. And the remaining, all the FPDs and those informations are pretty common. Plus it has the EOBC connectivity with the RP. Okay. For the control plane and the punt inject as well as for image download and for the other communications. This is the show control. 4 NPUs, right? So 0, 1, 2, and 3. You can have 4 NPUs here listed in the output. Then each NPU will have the 6 will have only 3 slices. Now, as this is the line card, you will have slice number 0, 1, and 2 programmed as a network facing interface, right? So you will have 0, 1, and 2 as an NPU core, plus as a PP port, which represents your interface group, you have 0 and 1. Okay, so that's how you identify it. Okay. So now coming to the 48 into 100 gigs. So 48 into 400 gig, like it has 4800 gig ports, plus it has capability of supporting MACsec. Okay, so you have a MACsec chip here between the NPU and the optics. Okay, for hardware level MACsec encryption. Okay, but 48 into 100 gig card can boot in the 5 fabric card system. Okay, so in case your router is running in 5 fabric card mode, then 48 into 100 gig card will boot in that. Okay, it will also boot in 8 fabric card mode, but like as I mentioned, 36 into 400 gig card will not boot in a 5 fabric card mode system. Okay, so it has 4800 gig ports, 2 specific NPUs, like it has 2 NPUs, 24 interfaces to each NPU, 24 into 100 gigs. Plus, it has a MACsec ASIC, which is from the Marvel, and it has the same P2PM connectivity to the RP and the other standard UBC switch and those. So now if you do show controller NPU VOQ interface all, instance all for the location, you will see 2 NPUs because 0 and 1. Then on the NPU core, again, 3 slices are programmed as a network facing. Remaining 3 are programmed as a fabric interface. Right? This output, like the fabric interface ASIC or the slices, you will see only in the show controller FIA and those outputs. That we will see when we are discussing the fabric section. Then the interface groups 0 and 1. So any questions on the RP line card? Okay. So coming to the fabric card, so we can have 8 fabric cards in Cisco 8000 series router. So your line cards are inserted horizontally on the chassis from the front, while your fabric cards are inserted vertically. To access your fabric card, you need to remove your fan tray. Okay, so now this is the diagram, like where one of the fan tray is removed, and behind each fan tray you have 2 fabric cards. Okay, so your fabrics are inserted vertically, while your line cards on the front are inserted in the horizontal fashion. So there is direct mating between the line card and the fabric. So there is no backplane as such in between for them. Okay, so there is direct connectivity. So it is a standard, like you have 8 fabric cards. If you lose 1 fabric card, you have N+1 redundancy to support full traffic rate. So just the that is front, the fabric card is inserted from the back, and it uses the same Cisco Silicon One ASIC. Only those ASICs are programmed as a fabric elements. And as I mentioned, if you okay, how much bandwidth? We will come to that. I have a slide for that. But as of now, we have 36 into 400 gig line cards, right? So per slot, it is having 14.4 Tbps of traffic per slot. Okay. If you lose 1 fabric card, then for each line card, you start losing 2.4 Tbps of traffic. So just multiply with number of line cards you have on the chassis, so that much bandwidth you lose. But we will discuss it when we are discussing the other slide. Okay, so this is just internal names of the chassis and the fabric cards. And as I mentioned, it uses the same type of ASIC that is specific, which is on the line card, and the same ASIC is used on the fabric card. So depending on the type of chassis, like 8-slot chassis will have a different fabric card. A 12-slot chassis will have a different fabric card. 18 slots will have different, and 4 slots will have different. Now, why they are different? Because they have different number of the specific ASICs on it. Okay. So like 8 slots will have 2, while 12 will have 3, and 18 will have 4. Okay. So what comprises of a fabric system? The fabric system comprises of the slices on the line card, which are acting as a fabric interface ASIC, and your fabric cards. Okay. Then on the egress card, again the fabric interface ASIC. So these 3 components together form your fabric subsystem. Okay. So the same ASIC is now programmed as a fabric interface ASIC, your fabric element, as well as the fabric interface ASIC. So that's how it is. So number of So the fabric cards are different depending on the type of the chassis. Like 8-slot chassis will have a different fabric card as compared to a 12-slot and 18-slot. Okay. They are all single stage fabric. Like it is not like in CRS you have S1, S2, and S3. Though the command CLI is similar to that, but still it is a single stage fabric. And it has connectivity like the fabric to the FIA, like from the line card to the fabric, those links are connected by a 50 gig internal SerDes links. So, but they can be even programmed for 200 gig based on the feature of this thing. So that leeway is available. Right now, they are all 50 gig. Okay. So this is the same diagram where the line card you have this is the NPU. On the NPU, 3 slices are programmed as a network. Another 3 are programmed as a fabric. And on the fabric, all the 6 slices are programmed as the fabric element. And similarly on the line card on the egress. Okay. So these are just the NPU. On the NPU, what are the different slice numbers? Like on LC, your slice on the NPU, slice 0, 1, and 2 will act as a network interface, while slice 3, 4, and 5 will act as a fabric of the FIA. Okay. While on the fabric element, all the slides 0, 1, 2, 3, 4, 5 will all act as a fabric element. So now this was the point I was talking with regard to the bandwidth. Okay. So we have a 36 into 400 gig line card, right? So now this line card has 4 NPUs. Okay. So it has 4 ASICs on it. Okay. So total like 36 into 400 gig, like if you multiply, it will come around 14.4 Tbps. So at a network, you can send 14.4 Tbps. But on the fabric side, like from the FIA to the fabric, okay, you have capacity of 19.2 Tbps. Okay. So from each line card, like for each NPU, 600 gig into 4, that is 2.4 TB goes to each fabric. Okay. Someone had questions regarding this, so this diagram will help in answering that. So even if you lose one fabric, like you have 0 to 8, right? So if you lose one fabric card, you will lose 2.4 TB of traffic per line card. So, but still, like from 19 point, this is 19.2 TB. So if you remove 2.4, it comes around 16.8. So it is still much higher than 14.4. Okay. But if you lose even further, then you might see, in case you are pumping full line rate, then you might see some packet loss. Again, I mentioned like 36 into 400 gig card can only work in 8 fabric card mode. Okay. And 8 fabric card mode doesn't mean you have 8 fabric cards. Cards, like you can, if you like 48 into 100, that is equal to 4.8 Tbps. But on you have 2 NPUs, right? 24 ports per NPU. So it is equivalent to 9.6 Tbps of traffic on the fabric side. So now coming to 8 fabric card mode and 5 fabric card mode. So like like on Cisco 8000 series, your hardware is optimized for LCs with 400 gig ports. Like for each FC is designed for 14.4 tera traffic from the LC as of now. Okay, but as I mentioned, currently the SerDes, that is the internal links between your fabric to the line card, are currently programmed at 50 gig, but they are capable of even getting programmed at 100 gig. Okay, but as of now, each line card you can pump 14.4 TB of traffic per line card. Then based on the type of platform and the number of line cards installed, that much traffic the fabric is capable enough of sending. Like line card can send 14.4 TB of traffic, but fabric can handle 19.2 TB per line card. Okay. So there is enough bandwidth available even if you lose one fabric card on the back, right? So with N plus 1 redundancy, you have good capacity. You can say the fabric is non-blocking this thing. But we will have more details whenever we are doing the section for the fabric. Again, with lower bandwidth cards like 48 into 100 gig LC, you can achieve the same with the just 5 fabric. You are having 48 into 100 gig cards. Okay, you have not installed any 36 into 100 gig cards or 400 gig cards, then you need not have 8 fabric cards installed in the chassis or run the chassis in the 8 fabric card mode. You can run your fabric in the 5 fabric card mode. So at a given time, only 5 fabric cards would be active. Even if you install, say if you change your chassis mode from 8, by default, as I mentioned, your chassis would be running in 8 fabric card mode. Okay, if you change it to 5 fabric card mode, at a given time, only 5 fabric cards will be active. That is FC1 till FC5 will be active, where FC0, FC6 and 7 will be shut down. Okay. So that is how you change from 8 fabric card mode to 5 fabric card mode. And this 5 fabric card mode is good enough to handle the traffic from the 48 into 100 gig cards. Okay. But in case you install a 36 into a 400 gig card in a 5 fabric card mode chassis, then the card will not boot up and you will get an error message in the log. Okay. So any question on this? Ashish, time check. Now this is how you change your fabric mode.
We have 15 minutes left, almost, including question answer.
Okay, I think we should be good. Yeah, I think we should be good. We have BMC, power, and optics now. So this is how you change your fabric card mode. As I mentioned, by default, your fabric is in 8 fabric card mode. But say your customer doesn't want to purchase all the 8 or doesn't want to populate all the 8 fabric cards, then he can run in 5 fabric card mode. So he can install, but restriction is we can only have 48 in 100 gig card on it. We can't use 36 into 400 gig card on the chart. So that's so to change from 8 fabric card to 5 fabric card mode, this is the command you want. If you want to revert it, you do no to it and commit it. But for whenever you are doing a mode change, you have to reload the chassis for it to take effect.
So, Anil, does it mean if a customer is buying this box and is going with the 5 fabric cards, do we need to by force make this mode to 5 FC or it should work with the default?
No, customer has bought with how many fabric cards?
See, he has got with the highest model and he has bought only 5 fabric cards which he wants to use.
Okay. So he has.
So,
Okay. So
does he
customer,
needs to make this
so,
changes?
Yes, yes. See, now see, as I mentioned, when you boot up the chassis, by default, it will boot up in 8 fabric card mode. Okay. Now, on the chassis, you have only 5 fabric cards. So you are nowhere near the N+1 redundancy. In an 8 fabric card system, you are already down 3 fabric cards.
Okay.
Okay.
So system is checking.
Still you are running in 8 fabric. Yeah. But still, you are in 8 fabric card mode only, and you are running with lower fabric capacity. Okay. On this state, you can still insert your 48 into 100 gig cards. You can still insert 36 into 400 gig cards. But in case you are populating all the LCs and you are pushing full line rate of traffic, then you will see traffic loss because you are at reduced fabric capacity. Right? Now, if the customer wants N+1 redundancy, even with just 5 fabric cards installed on the chassis, then he has to migrate from 8 fabric card mode to 5 fabric card mode. Okay. So he will do this config changes and reload the chassis. In that case, his fabric cards that are installed in slot FC1, 2, 3, 4, and 5 will be part of the 5 fabric card mode chassis. Your FC card in 0, 6, and 7 will be disregarded, like they won't be considered as part of the fabric. Okay. So even if one of the card goes down of FC1 to 5, and you have a spare card installed in SC6 and 7, still
that
those
will
won't
take
be
over.
used as part of redundancy.
This one got it. So ideally, if you are not changing this mode, even though the setup will work in case of worst scenario, just you mentioned, in case of failure, the setup will fail.
Yeah.
It is very
Not
much
even
similar
with
to the
failure,
Nexus
you
7K
are working on.
backplane. In the Nexus 7K backplane, now why I did ask this question, because in Nexus 7K we do have the similar parameters as you said, but there is no such way to modify the numbers of fabric manually. So I was just correlating with that.
So as I mentioned, like you have two, depending on, like you will lose redundancy in case you are not using in changing the modes. Because with the 48 into 100 gig cards, your system is good enough to handle full line rate of all the cards installed on the chassis with just 5 fabric cards. In case you are in such a scenario, you are good with 5 fabric cards and you run with 5 fabric cards. But in case you want to install 36 into 400 gig card, make sure your system is running into 8 fabric card mode, which is default.
Thanks, man.
Okay. Now coming to BMC. Now this is an important topic or component, and it is new to routers. Okay, and it is new to us as handling XR systems. This is the first XR platform to have a BMC interface. Okay, now a separate detailed session for BMC is planned in the next week. So I'll be just covering overview. So, but in the detailed session, a dedicated session for BMC is planned next. Okay. So now just an overview of BMC. Now this concept of BMC actually came to the routers from the server world. Now a typical data center customer, they actually, how do they monitor their servers? Or they access or they control the servers, they typically do using the BMC interface. Okay. So for what purpose do they use the BMC interface on the server world? So they monitor the chassis environment, the fans, the other environmental readings using the BMC connection. Okay. Plus, they, in case the server is down and in case they want to reload the server or reset the server, because in a data center you have lots of servers, right? But every server, they can't afford to send a field engineer for resetting a server and all. So they developed this concept, or it's now it's an inbuilt function now on the servers that they have a BMC chip on it with an interface which they control using their monitoring system. So via this BMC connection, they can monitor the servers as well as reset the servers without sending any field person on the site. Okay. So such functions they typically use. So as I said, this Cisco 8000 series router is a product common for the service provider environment as well as for the web customers or the data center environment. So this was one of the requirements from them to have a BMC interface on the RP. So that they can use the common tools by which they manage their servers. They want to use similar tools to manage the servers, the routers going ahead. Okay, so that was the background by which this BMC was introduced on the RPs. So you have a BMC interface on the RP, like on the active and on the standby. The line cards and fabric doesn't have any BMC interfaces as such. Okay, so now what purpose does it serve on the router? Now BMC is actually an ASIC on the RP. Okay, it doesn't run any XR software on it. It has its own software, like a Linux image on the ASIC. So BMC in itself is a system on a chip, which with its own software layer. Okay, the BMC chip talks to the XR CPU on the RP. Okay, and fetches all the power related, the environment related information and other control functions from the RP and pushes it back to the monitoring tools via which the BMC is connected. So that is one primary function by which customers are intending to use it. Okay, but that is for the customer. Okay, plus what is there for us? Okay, we as an engineer, how we can use BMC? Like we can say, for example, your router is hard down and your RP is not responding. Then we can use BMC as a back channel method to go and access the RP or the reset the RP or fetch data from the RP or log in into the RP. Sometimes your RP is booted up, but still you are not able to log in, right? So in such a scenario, we can use BMC as a back channel method to log in, okay? Or reset a particular line card. Say RP to LC communication has failed. So BMC has connection via the FPGA chip from the RP to the remote line cards and the fabric cards. So that such methods are also used. Plus, in case customer wants to reset or reload the router remotely, he can use the BMC. In case the router is not accessible via management or via console, he can still use BMC to access the router and reload without sending a field engineer there. So those are various use cases for that. So when you do show platform, you see on the RP you have a CPU 0, which is your XR CPU, plus you have your BMC. Okay. So it doesn't run XR software, as I mentioned. It runs its own Linux stack and application for BMC on it. So we as a software, what we install on the BMC is the FPD package. For us, it is like an FPD that we do for normal optics or those stuff. So similar things that we install for the BMC. So how can you connect to the BMC interface? So you can either connect to the BMC directly via console, like our XR console by default is connected to the XR CPU. The RP console is by default connected to the XR CPU. But if you press Control O, it will connect you to the BMC. Okay, so that toggle functionality is available. Okay, from the normal RP console, by default it will be connected to the XR CPU. But if you press Control O there, it will connect into the BMC. So that is one way. Plus, apart from that, there is a dedicated BMC interface on the RP, which you can allocate an IP and have an external dedicated connection to the BMC. Okay, so there are two ways how you can connect to the BMC interface. Okay, so as I mentioned, like this is the internal diagram of the BMC. Like BMC, as I mentioned, it's a chip which is running its own protocol or the software stack, which is not XR. So it has connectivity to the RP, it has connectivity to the FPGA. But normally it will talk to RP to fetch all the environmental related information from the chassis, the different line cards, fabric cards, power supplies, fans and all. It will talk to RP and take it and send it to the remote system. In case the RP is not responding, okay, then BMC can use the connectivity via the FPGA to reset the RP or fetch the data from the remote line cards, the logs and those stuff, it can fetch it. This is like a back channel method available for us as an internal and for customers also. Okay, this is just a screenshot of how you can do. Like when you log into the BMC, like say you log into the console of the router and you press Control O, you will come to the BMC interface. Okay. So it's a different, this is just an example. And then you can reset a particular line card and RP and those stuff. Or even re-image a card and those things. So these are the options used during disaster recovery or in typically say on a EXR system. Say if you lose your password, there is no option but to do an USB boot, right? So you can't recover the password on an EXR system, on NCS 5500 or other EXR system. So the only option was to do an USB boot. The USB boot option is still available here. Okay, so that has not gone away. You still have an USB boot option of re-imaging the whole chassis. Okay, but you have an option of using a BMC mechanism by which you can log into the XR by excluding your AAA session, and you can log in and reset the password. There is one back channel method available. Okay. So,
Last 3 minutes.
hello.
Yeah, last 3 minutes almost.
Yeah. Okay. So next is the power, fan, and EMON. So on a fixed chassis, you have two power supplies on the back and 5 fans on the back side. Okay. So there is one critical information, especially with regard to fans. So these are the systems which are running 400 gig optics. The heating is like cooling is a critical requirement for the system. So if you lose one fan, and the system is still fine. The other 4 fans are good enough to take to the cooling requirements of the system. But if you lose 2 fans out of 5, or then the system will shut down gracefully within 2 minutes. Okay, so there is one restriction on it. So coming to the power supplies, like on the top of the chassis, you have 3 power trays. Okay, so this is an individual power tray, okay, with 3 slots in it, and inside each of these power trays, you have your power modules, and you have a switch on the side at the tray level. You can power off an entire tray, but not the power modules. Okay, and this is the back side of the power module. Like, on the front side, you insert your power module, while on the back side of the chassis, you connect the connectors, the power cords. Okay. So this is the power module, and each of this power module, the one which is inside this tray. Okay. So each of this power module can take 2 inputs. Right? You can have redundancy with regard to inputs to a power module. Okay, so when you insert both the power cords or both the input powers to the power module, it can provide you 6.3 kilowatt of power. Okay, one power module. But in case it is inserted with only one input source, then it will provide 4.2 kV. So that is the difference. So you can have redundancy of input at the power module level itself. So we have AC and DC. In case you are having AC or hybrid AC-DC, then 3 power modules would be there per tray. In case you have having DC, then you'll have 4. So the system has the router or the card level, whether RP, LC, Fabric, they have a concept of power zones. Okay, there is nothing like a power zone at the chassis level. Okay, like some cards in zone 0, zone 1, no, there is no such concept here in Cisco 8000. But at the individual card level, there is a power zone concept. Okay, so whenever you insert the card or when the card boots up, so zone 0 will have your FPGA. Okay, the FPGA components of the card will boot up. Post that, your PCI switch, your BMC, then the CPU on the card, as well as the EOBC and those components will boot up. Okay. After that, once they are boot up successfully, then the zone 2 or 3 we can call will be the NPU. The NPU is the part of the last power zone. Okay. So that's how it is segregated. But this is, as I mentioned, it's at card level, at RP, at LC, at the Fabric. It's a common, like first FPGAs will boot, then your PCI switch, your EOBC, your CPU on the card will boot, and then your NPU will boot. Okay. Now coming to the fan trays are on the back side of the chassis. Like you have to, on the distributed system, you have 4 fan trays. Okay, and they would be marked like this on the back side, FT0, FT1, 2, and 3. And behind each fan trays, you have 2 fabric cards, FT0 and 1, 2, and 3. Like you have 4 fan trays, total 8 fabric cards. Okay, you have to remove the fan tray to access your fabric cards. So, so in case you lose a fabric, like say, for example, you are doing some activity and you remove the fabric card, one fan tray, you are still okay. Okay. But say you have removed one more fan tray because of some activity or something, then within 2 minutes, your system will power off. Okay. So one fan tray failure is accepted. But in case you lose more than one fan tray, then your system will power off. Okay. On removal of one fan tray, your remaining other fans will speed up their RPMs to the maximum, and they will. These are just the number of fans based on the each chassis. So this is a show environment fan where you can see your fan trays, 4 fan trays, their RPMs. Even your power supplies has their own fans. Okay. So this is just the fan failure scenario. Like you have removed one fan tray, then the remaining three fan trays will speed up to the maximum RPM, and they are still good. But in case you lose one more fan tray, then the system will power off. Okay. Then some restrictions with regard to, say, within a fan tray, though it is still inserted, some fans are not working 100%. And there are some thresholds for the speed up of the remaining fans. Okay, coming to the last section, that is optics. We'll have just 5 more minutes. Okay, so this is like on Spitfire. This is the first XR system to have a 400 gig optics, right? But we do support other apart 100 gig and 400 gig, which are there available with the cards. We do support breakouts. Like you can do a breakout of a 400 gig port to 200 to 400 gig port, or a 100 gig port to 240 gig ports, or 40 gig port to 410 gig ports. So those breakouts and those options are available. Okay. So this is just the information for reference. And the 400 gig optics, it is called as QSFP-DD. Like wherever you see QSFP-DD, then it is a 400 gig optics. Okay. It is also called as QSFP-56DD. Okay. So this is just those I have just highlighted this. Yes, it is full duplex. 400 gig is full duplex. Okay. So QSFP 50, this thing. So what platforms, in all the distributed platforms, we support 400 gig. That is, we have an LC 36 into 400 gig. In a fixed system, that is 8201, we have 24 400 gig ports, while 8202, we have 12 400 gig ports. So you can see the QSFP-DD, that is the 400 gig port. The XFP-wise, they are slightly longer as compared to your QSFP-28, which are your 100 gig. Okay. So, but you can, on a 400 gig interface, you can still insert an 100 gig optics, and it will still work, because internally it detects, like the pin structure is there. Like in case, like on a 100 gig port, it will be shorter, so it will detect the pin at a lesser distance, while the 400 gig port will get detected at the second distance. So auto detection is there for 400 gig, 100 gig in a 400 gig interface. And this is just the breakout information, like how you can use the breakout cables on a 400 gig port. You can use a breakout cable to break it into 400 gig ports. Okay, so there are some restrictions with regard to type of XFP that you can use on the breakout cable. So please refer the interface config guides and the reference for that info. Okay. So this slide actually summarizes the different optic types that are available for the fixed systems and the distributed system for 400 gig, 2 into 400, 200 gig, and 100 gig and 40 gig. Okay, so what are the different optic types? What are the different breakouts that we support on each of the interface? So for troubleshooting, you have your standard commands. Show controller optics is the command, as well as show controller 100 gig or 400 gig. Those commands are pretty standard that we have in normal 40 gig or 100 gig interface. The command wise, it is pretty much same. So your show controller 100 gig and show controller optics, and those commands are pretty similar. So that was my last slide for today. And I have put some references here, like we can use it later once the sessions are done. So, but I have put the links for the references from where the training slides were prepared. So if you have any questions, let me know.
Yeah, a little bit over the time. If you have a couple of questions, we can still take it. Okay, if there are no questions, probably we can conclude, and I'll share the recording and the.
It was wonderful
Thank you.
session, Anil.
Thank you, Anil. It was great session.
Thank you. Thank you. Bye.
Thank you, Anil.
Anil, it was a good session. Thank you.
You stop the recording.
Just stopping. Yeah.